Maybe we don't know.
But I mean, you can Yeah.
Okay, good morning. So this morning will be Professor Laumann speaking of quantum satisfiability.
Well, wow, thank you. I haven't even done anything yet. And I've already lost some number of people who didn't make it this morning. The decay has set in for the school, at least for the 9 a.m. or 9:30 lecture. So actually, I will probably get to quantum satisfiability. I'm sure I'll get to quantum satisfiability, but we're going to keep talking about complexity and go to the quantum case, which is the continuation of what we talked about last time. Okay, let's just dive right in. So what I want to do, we got to the, right at the end, running a little bit over last time, we did my sketch proof of NP completeness for 3 satisfiability. That is the Cook-Levin theorem. And with that, that's sort of the end of the tour of classical satisfiability, complexity theory that I wanted to do. So now I want to go to actually putting quantum in. Quantum complexity classes. And there's basically, very roughly, though the details change a little bit, you know, we had P, NP, and NP complete, and we're going to look at quantum analogs of those 3 classes. Okay? Roughly speaking means put a Q in front of everything. But, you know, maybe it'll be a little bit different. So the analog of classical easy is called, anybody know?
QP. Oh.
BQP. Okay, and I'll tell you what that means in a minute. A decision problem, L, is in BQP. If there exists a quantum polytime or poly-size circuit, polytime algorithm that can solve, decide L with bounded error rate. So does anybody know what the B stands for?
Bounded.
Bounded quantum poly. There they are. Okay. So this is a little bit more complicated than what we defined for P. The first part looks sort of like the right thing. Instead of having a classical poly-size circuit or polytime algorithm that can decide L, that is, you give this circuit an instance, X, and it says yes or no, decides if it's a yes instance or a no instance. Now we have a quantum polytime algorithm or poly-size circuit that can decide L, but we had to introduce this complication of a bounded error rate. Why? So why do we need to complicate our lives?
I mean, presumably because we want to do a computation that can actually give us an answer with low chance of error, right?
Right. Well, for defining P, I didn't even need to worry about error.
Yeah, so for that, I would actually have a question then. Why is error considered here? That seems to be more like an issue with implementation rather than in like some particular physical system rather than an algorithm itself.
Classically, there are some yes and no things.
Sorry?
Classically, they had only yes and no. Here, you can have a phase.
You can have a phase, but actually it has less to do with the error in, I could imagine that I can make ideal quantum circuits. Let's assume, which is what we're going to do for most of today, that we're thinking of building quantum circuits, which means what? It means we have a bunch of qubits, and we hit them with pulses, which we think of as being circuits, or sorry, gates acting on them, causing unitaries to happen. And I can do that ideally. And there's not even any extrinsic noise. There's nothing kicking it, right?
Just because of the intrinsic nature of the quantum mechanics, the superposition of different states, right?
Well, it's something intrinsic about quantum mechanics, but not about superpositions per se.
So it's approximately, so the gate, the algorithm just approximately mimic the gate, right? The operation, you can only approximately to realize it.
No, as a theorist, I can assume that it's exactly what I want.
Okay.
Can't do it if you're an experimentalist, but
To get the result out, you have to make a measurement, and you don't know which of the states you're going to measure.
that's right. So in quantum mechanics, at the end of the day, say that I have let's think what a circuit looks like in very high level black box picture. I have qubits, here they are. I have, this is, if you want time, I have a set of gates, something like this, which, depending on your implementation, might be pulses or whatever, but they're, there's something that happens to your qubit of quantum information. And at the end, you need to learn like what's going on in this thing. To get a yes/no outcome, you have to measure something, right? And the measurement, there's my measurement. See, it's like an eyeball from the side in cross section. This would be really painful if it happened to you, right? Okay, so anyway, this thing is a measurement. And of course, we know that in quantum mechanics, measurements come from the Born rule, which is that they happen, you get yes or no with some probability, which is an amplitude squared of the final state, right? And you could define a class where you weren't allowed to make any errors at all, that it was always perfect. But then you would almost certainly not be able to do very much with it. Actually, it's an interesting question. I don't know what you can do with it exactly.
So I'm a little lost because I'm imagining if you get an answer at the end, some circuit,
Yes.
can't you always just rotate whatever it is into your measurement basis? And then
Well, so, okay, so what happens? I have some fiducial starting state, or maybe it's X. I describe the input I want, or the instance. Or X might be built into the gates I choose, so there's a couple different ways to do it. And then at the end, there's some state psi at time t, right? And I'm going to do a measurement. And if I knew exactly what psi was, why would I have done the computation? So I need to learn about it. And that I can only do by making measurements. I don't necessarily, what I want is that, and this is where the bounded comes in, what I want is that if I put a yes instance here, at the end, the probability of yes given it's a yes instance, right, is greater than 1 minus epsilon for some error, which is bounded, and probability that it's no given that it was a no instance in is greater than 1 minus epsilon. They don't have to be the same, but say greater than 1/3 or greater than 2/3, something like that, some bounded error. Does that make sense? Because now what? So if I have this problem, I can put it into my quantum computer at the end. something happens, I don't know what's in this state anyway, I make a measurement, I only get some probabilistic outcome of yes or no, even if it was a yes instance or no instance, but I want that to at least be significantly biased in the right direction. And if it's biased in a bounded way, then I can just run this independently. I can just run it again, do the whole thing again. And every time I do it, if it was a yes instance, the probability that I get the wrong answer for all of them is, going to go down exponentially, right? So,
Yeah, are there realistic cases where the bound is terrible? Maybe this is similar to asking about polynomial algorithms with a terrible degree, but are there any constraints on how good the bound actually is?
yeah, so, okay, this is usually defined with some number, like 2/3. But actually, so long as the bound, this epsilon, is better than, so it needs to be greater than a half plus delta. I mean, if it's a half, you're screwed, right? But it needs to be greater than a half plus delta, where delta is at least 1 over a polynomial in the input size. So it can be just a little tiny bit better than a half. And then the thing is, by doing the whole circuit repeatedly, you can amplify that, so long as it's not itself only exponential, tiny, like it has to be at least 1 over poly bigger than half, and then you can amplify it with only polynomially many tries. If it's only exponentially above, then you would have to do this so many times that you wouldn't be able to, in the end, get it to be poly. Okay. Okay, so wait, was that clear to everybody? What do you do to do it multiple times? If you have, actually forget the quantum mechanics for a second. If you just have a box and every time you hit it, it independently gives you, oh yeah, that's a yes instance or that's a no instance, and its probability of doing it is only a half plus a little bit correctly, then what do? You hit it and get the answer 10 times or 11 times, and then it says yes, 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 no, no, yes, no, no, yes. You take a majority vote, and that's much more likely to be the correct answer than any of the individual ones, right? We won't quantify that amplification here, but you can. It's straightforward statistics, and the same holds here. So long as this thing is a little bit better than a half, and by a little bit we need 1 over poly, then you will be able to amplify it by at most polynomially many repetitions to say be arbitrarily close to 1, whatever your tolerance is. Okay, 0.999. So that's why we need the bounded error. Yeah.
Just to clarify, the error only comes into the problem at the very last measurement.
So the question is, maybe the question is, can I build something here? At the end, all I'm going to get out is a yes or no, but I'm going to allow that it's not completely deterministic. Given a particular input, it could give me both outcomes. And maybe other stuff happens. Okay. Now, why? Now there's a question of what you mean exactly by a quantum polytime algorithm, which I haven't defined very carefully. I like thinking in this idealized setting of just there's a unitary circuit with a single measurement at the end. And that's actually kind of equivalent to most other things you could do, because if you had intermediate measurements, you can, in general, rearrange the circuit to push them all to the end and make it all controlled gates. So if you had intermediate measurements with conditioning on them, et cetera, you can, in principle, make it look like this. It's not how you would necessarily implement it. But at the end of the day, it's you have something input, which is the instance, some quantum stuff, allowing unitary evolution, and also measurements in general, but both types of things, happens. But at the end, I just look at one bit measurement, one particular measurement at the end, which is a bit, and has some distribution that I want to satisfy these constraints. Okay. So this is, I guess it's true. So this is not to do, this is not particularly to do with extrinsic noise, right? And that's something you would deal with error correction, et cetera. But if I can do this in the ideal case, then in principle, I can use error correction to do it with good enough gates in the not ideal case as well. But even in the ideal case, I have to allow that quantum mechanics only gives me probabilities.
Yes, like if it like proves a certain algorithm, it might not be exact for like more than 4 objects.
Sorry,
It's only exact,
Grover's.
It's only exact when there are 4 objects it searches.
But so that's,
So
okay.
this kind of error is also included, allowed in this.
Yeah, so in Grover, for example, yeah, you're right. So you're in Grover if you, sorry guys. So in Grover, if you have 4 objects, it turns out there's a rotation you can do, and if you have ideal gates, which gives you probability 1 of getting the right answer after whatever, 2 steps, 3 steps, something like that. And if it's not that, then you don't hit it exactly, but your probability of getting the right state becomes close enough to 1 that you can use the algorithm. So that's the same error, essentially here. Okay, so that was a long digression, but I think it was an important one. So what is the example? Like the reason you guys are in this room. You don't know this, maybe. Maybe some of you know this. But at like a fundamental level, what is the example?
Factorization.
Factoring. Sure, 94. I say that you're in this room because of that. Maybe you don't care about factoring at all. Maybe you've never heard of factoring. Maybe. But this is funded on a global scale, right? The reason that there was a lot of research in quantum computing starting in the 90s was because of this. And that's why there's a field, I think is not totally unfair. So what is factoring? Well, we need to state it as a decision problem. Does some integer n have a factor p with 1 less than p less than m, where m is some other integer? So this is a yes/no question. This is not exactly finding the factors. Actually, Shor's algorithm does find the factors. It's how it would answer this question. But if you can do this, then by varying m and asking the algorithm over and over, you can do 20 questions and find factors as well. So, in principle, this is equivalent to. And so maybe I know that I'm not supposed to put things over here, but I just want it kind of out of the way. So is it okay up here? You guys can see. So here's P, right? Factoring's in NP, because easy to check. Multiply, or sorry, divide. If you have a factor, you take n, divide by p, and see if it's whole. So it's easy to check, so it's an NP. So NP, here's factoring, right? And maybe I'll draw it over here, factoring. And here is BQP. Okay, so factoring's in BQP. It's in NP. So in NP, it is unknown if it's in P. Because we don't know an algorithm to do it in poly time doesn't mean there doesn't exist an algorithm, right? So this is kind of the conjectural picture. Why did I put P inside BQP?
Always run a classical algorithm on here just by using gates that are like X, Z.
Yeah, exactly. So classical algorithms are quantum algorithms. They're just diagonal ones if you want. And they don't even have an error rate, so this bound is easy to satisfy. At least the ones in P don't. I should mention there is a class, which you guys kind of probably know. If you have Monte Carlo algorithms, they also can be have stochasticity in their output. And if you have something which with bounded error rate but with random numbers gives you answers, it's called that's a classical complexity class called BPP, which is a closer analog of BQP, but not so crucial. P, BQP, factor, and I drew BQP sticking out the side of NP because actually it's not really clear.
I'm sorry, I don't see why factoring is not in P. Why can't you just take every number between 1 and n and try to see if it divides?
So what's the input size?
N?
How many letters or bits do I need to specify an instance of this? Log n plus log m, if I specify it this way, right? And m's less than n, so basically 2 log n, say.
Yeah.
Okay, so how many numbers do I need to check if I check every number between 1 and n?
N?
Yes. And how big is n in terms of log n? Yeah. N equals e to the log n. So that's exponential, because this is the input size. Right? But checking it is fine, because long division, for example, was a polynomial algorithm in the number of bits, the number of digits. Right? Okay. So I think that's all I want to say about BQP. So what's the next class, which we had classically? Yeah?
Did you say it was known whether BQP is not P?
Nothing is known. No, wait, sorry.
Okay.
Whether BQP is not P? Is it bigger than P?
Yeah.
Well, factoring seems to be an example which is in BQP and may not be in P.
I believe you. I was just wondering what the state of knowledge
No,
is.
no,
They could all be collapsed, is that right, or no? Or is there something
So it's
that's not
always
collapsed?
possible. No, but it's very hard to show these classes are different. It's believed that they are different. So the reason I say that is because you could always maybe find an algorithm in P which does this thing. And that's why I said this is actually unknown. So, okay, maybe I can just say a few words about that. So until a few years ago, there was no deterministic algorithm for checking if a number was prime, not a poly one. It was only discovered maybe 5 years ago. I'm not exactly sure. So checking if a number is prime is obviously closely related to factoring. There was a stochastic algorithm, which is in fact how your computers generate prime numbers for doing cryptography. You generate a random number, check if it's prime using these random algorithms, and they were good. They were very efficient, but they were randomized. And nobody knew if there was a deterministic P algorithm for checking primality. And then it was discovered. I don't remember by who. I think the initial runtime was end of the 12. So it was still better to do the randomized algorithm. But end of the 12 happened, and now it's gotten better. It's somewhat, I don't know what it's down to, but it's better than end of the 12. So that's primality testing. Was until a few years ago not known if it was in P, but there was kind of a clue that it was because it was known to be in BPP, this randomized algorithm class. So now factoring doesn't have a good randomized test that we know, and it doesn't have a good non-randomized test that we know, but it has a good quantum test. And I don't think anybody knows how to turn this, or has any clue how to turn this quantum test into a classical test, but it doesn't rule it out. I mean, the fact that primality testing can be done suggests that maybe factoring, which is obviously closely related, might also have enough structure that there's a classical way to solve it. But I have no idea. So does that, so it's really unknown, and I don't think it's out of the question that it's in P.
Does factoring give us anything other than breaking the most common forms of like encryption?
You don't want to know what the factors of really big numbers are? I mean, that's the big application. So it's not exactly factoring. There's a, what actually Shor discovered was the quantum Fourier transform. I'm not, we're not doing this today, but it was a quantum Fourier transform. It has a bunch of applications like factoring, which have to do with what's called the discrete logarithm problem, and it breaks a bunch of crypto schemes that we currently use. There are other schemes which aren't susceptible to this attack. So the other thing, of course, is that at the rate things are going, by the time we build a quantum computer, we'll just switch everything onto a scheme that we don't know how to break with a quantum computer, and then it'll be okay. Okay? So certainly by the time you can build one that can factor a number bigger than, say, 15, which has been done. Is there any other reason you'd want to know how to factor? I don't know, just for sheer beauty of it. Yeah. Okay. Good. So what's the next class? Well, last time it was P and then NP, and NP was you could check things in polytime with a classical verification circuit. So there's an exact analog of that. It's called QMA. And okay, a decision problem, L is in QMA if there exists a scheme. These are my nice Weasley words, not to write lots and lots of formal nonsense. Exists a scheme by which yes instances may be checked. How do I write it? By a bounded error rate, quantum, polysize, polytime, quantum algorithm. Okay. Quantum verifier, I guess. We'll call it a verifier. Okay, so here the Q is clear. The M and A is non-mergers and acquisitions. What is it? M A. Do you guys remember the goofy picture I drew last time? So Merlin right? Merlin. Produces, he's still a yes man, and he advises Arthur. Excalibur. Right? Arthur has to have a sword. So Merlin advises Arthur. He likes telling him yes to everything because he's the king, right? And Merlin is very powerful. He can produce quantum states, which are witnesses or proofs for the claim that some instance is a yes instance of a problem. But Arthur is, well, we all know that King Arthur was honest. And he's fallible, right? He's only human after all. Right? And he's also skeptical. So what he does is, and this is where Excalibur comes in, he has a quantum computer. Okay? He's human, but he has a quantum computer called Excalibur. And he takes this and he puts it into his quantum verifier. He takes proof state, so witness state, we'll put it here for Merlin. And he also has to have give it some ancilla qubits to initialize it. This is his quantum verifier. which is poly size. And at the end, he does a measurement, and this is accept or reject the claim that the instance was a yes instance. Quantum verifier for instance. X. Right? So it is actually quantum Merlin Arthur. I'm not making it up. That is where the acronym comes from. This is actually, I really like that because I get to draw king. And the accept and reject have to be with bounded area, right? So again, we can say that this is, if it's a yes instance, then what does it mean? If it's a yes instance, then there exists a state, which is the proof, which is correct. And therefore, if Arthur feeds that state in here and runs his quantum verifier, then he will measure accept with a probability 1 or greater than or equal to 1 minus, sorry, I guess 1/2 plus 1 over poly, something like that. And if it is a no instance, then whatever state he puts here, his verifier will reject it, say that's an invalid proof. Similarly with a probability which is bounded away from 1/2, so that he can learn from it. Okay? So, what's an example? Well, the closest analog of, or the maybe canonical example, which we will simplify a little bit later, is called K Local Hamiltonian. And that's this question. Does H, which is equal to a sum of, how did I write it? Yeah, sure. Local terms, does H equals this have a ground state, yeah, okay, have a state with energy less than E? Okay. And there's a couple of caveats here. So, one, this is K, this is a general quantum interaction, but it only acts on, so K local means K, say, qubits are involved in this interaction, right? So actually this is a small literature point. K local in the quantum information literature has nothing to do with what a physicist means by locality, which means that this degree of freedom is near that degree of freedom. It means that it could be an arbitrary distance, but it only involves up to K degrees of freedom, which in physics would usually be called something more like K body. So you have 2 body interactions, 3 body interactions, et cetera. So this is what K local means in this context. And there's a promise here. I'll explain what that means in a second. Either yes, or all energies, so the ground state energy in particular, greater than E plus delta, where delta is 1 over poly. I'm down in a corner, you guys can't read. I apologize. Okay, so let's unpack that a little bit. We need some space. Where did all of this come from? Okay, so, what is an example here? Maybe just to illustrate. So the idea would be that I have a Hamiltonian. The Hamiltonian acts on some n qubits or n degrees of freedom or quantum like this. Let's say k equals 3, for example. then each term, hm, is some, acts on, say, 3 of those degrees of freedom. Okay? So this is an h1, that's an h2, and this is, say, a qubit. So I'll put a little hat on it to indicate it's quantum now. Okay? And what the question asks is, does this Hamiltonian, which is a sum of these terms, have a state with energy less than E? So why is that a QMA problem? Said it was an example of a QMA problem.
So if you're given a state, you can just compute its energy.
Yes, you have to somehow measure it. So if Merlin can come up with this state magically, it's a quantum state in general, what you want to do is compute its energy, or measure its energy somehow. So you need a box which can do that measurement, right? We're not going to talk about how to actually build that box out of, oh, I erased it, out of gates, but it can be done. But it's not surprising. I mean, measuring energy seems to be a natural thing you can do in quantum mechanics if you have a Hamiltonian in a state. But okay, you can do it. And if you measure it, and then at the end of the measurement, you check is it less than E, you accept or you reject. Now, can anybody figure out why there's this weird promise? So promises have a strange role. They're actually important in complexity theory. They basically are saying, this is my question. However, I promise that you won't need, I will never ask you an instance which doesn't satisfy the promise. And so if your algorithm doesn't work when the promise isn't satisfied, that's okay. Okay? So why might I need this promise? That either the Hamiltonian will be a yes instance, or the ground state energy will be at least E plus delta for some delta, which is more than 1 over poly.
So if you allow delta to be arbitrarily small and exponentially small, and you think about how a physical quantum system would actually implement this Hamiltonian, then for the Hamiltonian to relax to a ground state, for example, when there are states of E0 plus some exponentially small delta that are also in the space, that's going to sort of push that relaxation time exponentially far out.
So that's close, but we're not going to relax anything. Remember, we don't have to find this ground state. All we have to do is, when given it by Merlin, check.
So I think the analog for a quantum computer in the gate picture would be that the error probability from the measurements, that sort of, you want, so that it would have trouble reaching the bounded error condition, because you could make a measurement essentially arbitrarily close, and then you can't really distinguish those outcomes.
That is right. It'll have a problem with the bounded error condition. So, but there's a very physical reason.
To measure a certain energy splitting, you need time h bar over the splitting. So
exactly.
Exponential.
So, I mean, I didn't tell you how we're going to implement that box, but it's actually a very general principle of Heisenberg uncertainty, right? Time energy uncertainty. So, I don't know where to write it. Time energy uncertainty means that it will take t greater than of order 1 over delta to resolve energies that are different by delta, right? So if I give you an example whose ground state energy is actually E plus very, very small, I would need to run for time 1 over very, very small in order to be able to tell that it wasn't actually below E. You know, I couldn't resolve it well enough. And so that's why you need a promise that that gap is only at most polynomially small, because then you can run for a time which is polynomially long and resolve it. Okay. I'm stating this as if it's obvious. Of course, without knowing how this box works, you might think, oh, maybe I can evade this. It's not true. You can't. You really can't evade that. All the algorithms, they're called quantum phase estimation, which do this today in a gate model, they actually take a number of resources which scales with the precision to which you want to do the energy measurement in this way, consistent with time energy uncertainty. Okay? So, okay, good. So anyway, this thing is QMA with this promise. It turns out that this is actually a QMA complete problem, which I'm not going to exactly show you. I'm going to show you something closely related, a slightly simpler version of this problem, which is called quantum satisfiability. KQSAT as opposed to KSAT or K local Hamiltonian. This one is almost identical. It's just structurally a little bit simpler. So here the question is, well, I'm going to write it a little bit more formally. Input is a quantum Hamiltonian. H is, again, some m equals 1 to m, some number of terms, pi m, composed of m projectors, each acting on less than or equal to k qubits, or k degrees of freedom, out of some n qubit, out of n qubits, okay? And there's a promise. H has an E equals 0 state, or all states have E greater than delta, which is 1 over poly. And the question, well, which case is it? Does H have an E equals 0 state? This is called a satisfying state. Okay? So that's clearly very similar to the K local Hamiltonian problem. All I did was, what? I turned these into projectors. What's a projector?
An operator that squares to itself.
Yes, pi squared equals pi, and it's Hermitian, as most Hamiltonians are. So it's a Hermitian operator that squares to itself. That means it projects, you know, onto some subspace. Its eigenvalues are what? 0 and 1, because they have to satisfy the equation pi squared equals pi. What are remarks? this Hamiltonian, because it's a sum of projectors, is in fact positive semi-definite, which means that its spectrum is all non-negative, right? It could have zeros, but otherwise it'll be positive. It is specified in of order m bits, because I can specify each of these terms with a matrix, which is, say, 2 to the k by 2 to the k, right? But k is not allowed to vary with m, so that's just a constant with respect to making the system bigger. And m itself, well, is going to be no bigger than n choose k, because that's the most number of interactions I could have. So it's order m, or it's poly in n, yeah?
Doesn't the Hamiltonian sort of manifestly satisfy the promise?
No. So why do you think that?
I mean,
so the promise is
energy less than 1 for this Hamiltonian.
So the promise is that either there's a zero energy state, which is what we'd like to know, or all the states are not just strictly positive, but positive above a little gap. So this has nothing to do with them being negative, right? So the case is that if it's satisfiable, then here's the energy spectrum. Here's 0. There's a state at 0. Then there are lots of other states, right? But there's at least one at 0 if it's satisfiable. And if it's not, it has to satisfy the promise unsat. If this is the 0 level and this is delta, that means that there are no, I mean, maybe there's even above delta a gap, but there's no states in here. And that isn't manifestly obvious. So, and again, it's actually, it's the same thing. Energy time uncertainty means you can't check this 0 energy condition to better than this precision delta. So you need to have, in a time 1 over delta. So you need to have a polynomial promise on delta, right? Good. Oh, right. So why is this called quantum satisfiability? Well, this is really a kind of direct quantum generalization of classical satisfiability. In particular, if these projectors are diagonal on the computational basis, then it is exactly classical satisfiability. It gives an energy 0 to, each term gives an energy 0 or 1 to configurations that have to do with the bits that it acts on. Is that clear? So this, contains ksat, classical, no q. Just take pi diagonal in computational basis, or z basis. Okay. So, why did I pick this one? It's actually easier for me. When do I have until?
10:45.
Oh.
So another 25.
Huh?
Is that 25 minutes?
25. Ah, it's so much time. Oh, great. I'm going to just beat you guys into the ground. Bet you're ready. Okay, here we go. So why did I pick this one rather than Local Hamiltonian? Just the arguments to show that it's QMA and QMA complete are very slightly simpler. So that's why. Also because I really like this problem. I've studied it, the random version of it, for a long time. So we'll talk about that more after we've done this worst case part. Okay, so first of all, actually I should be a little more careful. KQSAT is in QMA, there's a little 1 there. What that means is that there's one-sided error. You can accept, there's this equals 0 condition, because this is positive semi-definite. You can actually check with an algorithm that makes no errors for yes instances. but in the no case, you have to allow error. So it's one-sided error. Okay? So let's show it a little more carefully. There exists a verification scheme such that yes instances, so satisfiable Hamiltonians, have verifiable proofs with a quantum computer with perfect acceptance, and 2, no instances always get rejected. With probability greater than or equal to, what do I want? 1, oh, get rejected. Actually, in this case, so because it's one-sided error, with probability epsilon greater than 1 over poly. So here, because I know that yes instances have perfectly verifiable proofs, if I reject even once, I can just reject and say it's a no instance, right? Or not say it's a no instance, say that's an invalid proof. And that means that I can have even a very small rate of rejecting bad proofs. Like if I'm not very good at telling they're bad proofs, that's still okay, because if it's a good proof, I will always accept it. So that's part of why this is a little easier to show. So what does Merlin do? How do we do this? Well, Merlin provides psi such that h psi is 0. And what does Arthur do to check? This doesn't require all the complications of full energy, time, uncertainty, phase estimation, etc. Arthur checks like this. He picks 1 of m pi little m randomly, and measures it. So in this case, he's also lazy, because he's not even checking all of the terms. He only checks one of them. Okay. You can check all the terms. This is a simpler proof. So where do you go? Indeed, where do you go? I'm sorry. So in the case that it is a yes instance, well, let's just look at what Arthur checks. So he measures this thing. So what does he do? So what's the probability that Arthur accepts, right? Well, it's the probability that he accepts, so he's doing this measurement, given that he measures whatever, the mth one, times the probability that he measures mth, right? And then sum over the choice of m, right? That's just conditional probability. He decides to measure m, and then given that he measures that one, what's the probability that he accepts, right? Well, okay, so the probability that he picks the mth one is just 1 over capital M, right? Sum over little m. And what's the probability that he accepts given that he measures that one? Well, now there's some quantum mechanics that has to come in here. How do we get this probability? It's the probability that pi sub little m is equal to 0, i.e. that when you do the measurement of pi sub little m, you get 0 on the state that was given, right? So what is this? Psi. So if I want this to be 0, I need to look at, okay, I could even write it so it looks really like the standard Born rule. So I need to look at the eigenspace, the 0 eigenspace, because this is either 0 or 1. This is a projector onto the 0 eigenspace. I hit my state psi with it, and I take the norm square, and I get 1 over m, sum over m, psi, 1 minus pi psi. Square of a projector is a projector. This is a 1 minus which is, okay, so 1 over m times the sum of m of 1 is shockingly 1, minus the sum over m of pi m is the Hamiltonian. There's like waves of silence here. I'm not sure if you're thinking or sleeping. Anyway, so if it's a yes instance, and that was a valid proof, then h psi is 0, and the answer is 1. So my probability of measuring a 0 is 1. Okay, we didn't have to do that whole calculation to see that. But what's nice is that by doing this calculation, we see what my probability of measuring 1 is for the no instance. This is 1 minus 1 over m times the energy of the state that was handed to me, or the expected value of the energy of the state that was handed to me. And because of the promise, I know that that is always, for no instances, greater than or equal to delta, right? And so this is always less than or equal to. So this is the probability that I accept. I don't want it to be 1. I want it to be strictly less than 1. So it is, okay, maybe I should, since I want strictly, it doesn't matter because delta is non-zero, but we'll just write it like that, less than 1 minus delta over m. And that means that my probability of accepting a bad proof is actually pretty high. But it's still Pauli, because m is the input size, so this is just one more factor of m. It is still Pauli bounded away from 1, which means that I will, if I do this enough times, reject reject bad proofs. Okay. Okay, now the much more fun part. Q set is complete for the class QMA1. Okay. Yeah, we'll do it.
If you measure that effect, you'll get 0 or something non-zero. It's basically just doing this sort of back and all the objectives. Sorry, so What was the point of doing this instead of just measuring the energy? Do you actually gain from?
Oh, how do you measure the energy? Okay, so it's mostly that in this class we haven't talked about how to measure the energy. How do you do it? You don't actually have. Actually, it's a general question. How do you measure the energy? Right. So it depends on your system, but if you're thinking in a circuit model, the answer has to do with an algorithm called quantum phase estimation, which, is a long detour from what we've actually covered. Because you have this state, you have a Hamiltonian. Let's be clear about something. The problem is not given to you as here's a physical system which implements some Hamiltonian. It's given to you as here is a set of matrices, 2 to the k by 2 to the k, which have these entries, and which you need to add up, tensoring on lots of identities, which in principle would make a very large, exponentially large matrix, right? And you want to know, does it have a zero energy ground state or not? But in principle, you could make this exponentially large thing and diagonalize it, but that you can't do in polytime. So it's still given to you as a classical sort of thing. I could write it down in reasonable size. But to check the answer, I need a quantum computer to do, basically, I need to be able to work with quantum states, because I can't write down the ground state necessarily without being able to write down exponentially many amplitudes if I do it classically. That's why this problem is quantum, if you want. And it's quantum to check. But then if I have a quantum state and I have this classical description of a Hamiltonian, okay, then it's still a non-trivial step to say, how do you get from classical description of Hamiltonian to measuring energy of a state with respect to that Hamiltonian, right? So mostly, this was a way for me to dodge having to go through that big detour. This isn't even, actually, you can even do better just by measuring these projectors, more projectors. You don't have to do this crappily, but this is the easiest one to analyze. And it doesn't change things up to polynomials. So I'm exploiting our interest in polynomials.
How do you quantify the input size for these types of Hamiltonian problems?
So it's the number of classical bits that I would need to describe that Hamiltonian to you.
So it's log of the dimension.
It is log of the Hilbert space dimension, yeah, Hilbert space dimension. But it would be if there's n bits, and like I said, it's basically the number of terms. So each term in that Hamiltonian you can describe in a constant number of bits, some fixed size matrix, and there are m of them. And so it's of order m is the input size. And that typically you would say is like at most quadratic. If it was all pairwise interactions or all cubic, three-party interactions, it would grow maybe cubically with the number of bits in the system. So that's still polynomially related. But it's simplest just to say it's of order the number of terms, right? But I don't have, the number of terms is still log of the total dimension of the Hilbert space. Okay, so QSAT is QMA1 complete. What does that mean? I didn't exactly, whoa, okay. Time flies when you're having fun. Okay, I better hurry up or we won't finish this. So, what does it mean? It means any decision problem B in QMA1 reduces to I'm going to say KQSAT. We're not going to get down to 3. That's actually a hard proof. Reduces to KQSAT. So I will just say that this is for k greater than or equal to 4. This was shown by Bravi 06. And for k equals 3, this is Gossett, Nagai, 2013, I think. And by the way, for k equals 2, it's in P. You don't even need a quantum computer. You can just solve it. Okay. So we're roughly going to follow the Bravi level 1, but I'm not even going to show you why it's 4. We'll just get to k. So, okay, so any decision problem B in QMA1 reduces to KQSAT. This is analogous to what we said about NP completeness. Any decision problem B in NP reduced to 3 satisfiability. What was the structure of the proof of that? The Cook-Levin proof or theorem was that I could take any decision problem's verification circuit and turn it into an instance of 3 satisfiability, which encoded the operation of the circuit, right? So somehow I want to do the same thing here. But it's a little more complicated. So again, I'm going to take the verification circuit, but now it's a quantum circuit, and reduce it to KQSAT somehow. Okay? So let's draw a verification circuit. So here's a gate. We'll call it U1. I'm just going to order them in some way so that we do them sequentially. U1, U2, U3, dot, 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 U capital T. There's some qubit lines. Okay. At the end, we say measure this one. This is our accept, reject. What do we put in at the beginning? Well, we need the proof that Merlin provides. I'm going to call it, I'm going to call it W for witness. So proof/witness. Okay, provided by Merlin. Then we need some extra initialized ancilla qubits. These are work qubits. There's a fundamental reason you need them in a quantum circuit because of reversibility, but we'll leave that aside. So we have, this is sort of the general structure. Good. So this is our quantum verification circuit. The idea is we put a proof here, we initialize these to 0, we run the circuit, we do a measurement, and if it was a yes instance and we were given a good proof, we will have a probability 1 actually of accepting it. And if it's a no instance, we'd be guaranteed to have at least some small probability of rejecting it. Okay? And now, in the classical proof, I looked at this circuit and I said, well, and I didn't even comment on it. I can label the state of every wire in that classical circuit by a bit, which is, sigma I at time, right? And this would be, say, ±1 or 0 or 1, right? Some bit. But how do I do that quantumly? Because here I can have some complicated entangled state here. It doesn't necessarily just have a local bit on a particular line. Okay? So I'm still going to introduce time. Here's a time axis. 0, 1, 2, 3, T. Okay? So the configurations in the classical case, I could. In the classical case, I could say that there was kind of a space-time history of a classical computation given by sigma IT, right? And if they didn't satisfy the gates, it was an invalid history, but that was one way to think about it. I had a full set of these variables, and that gave me a history of the computation. So how do I want that again somehow. And the, and in that case, the ground states of the Hamiltonian or classical Hamiltonian we eventually constructed corresponded to valid histories of a computation that was accepting at the end, right? Those are the zero energy histories for 3-sat. How do we do it quantumly? This is what's called the Feynman-Kitaev history state, or history state construction. So Feynman 82, Kitaev turned it into this kind of beautiful proof, I think 97 or 99, a little unclear. What is the history state? Here's a state. How do I want to write it? Yeah. Okay. So the idea is that, indeed, I can't write just a sigma IT, which is a bit for each line. But I can, at any given time step, I do have a state. There's a psi initial, psi 1, psi 2, psi 3, right? And here I've made one quantum state of some bigger system, which has in superposition the entire history of the computation. Okay?
So the psi is the product of all those different lines, all the entangled states, just expressed.
The psi, yeah, so the psi is the, remember what I basically have is a system, in this case of 1, 2, 3, 4, 5 qubits. And at time, you can really think of this as time. So at time 0, they're in the state psi 0. Then I apply this unitary U1. So they're at time 1, they're in state psi 1.
Oh, for all times.
All of them. And so this is actually equal to.
I see, so this really is the entire history of this.
Tensor. ut minus 1 u1 on, we called it w comma 0, 0, 0, whatever the input state was. Okay, so that was the intermediate state at each stage. So what are the pieces of this? This is obviously, as we just said, state of n qubits at time t. This is the what's called position or of a clock particle. And this is, of course, just normalization. Okay. Okay. We'll stop here because I'm out of time. So I'll just say, so what this is telling us, and I'll let you guys ponder it, and then in my next lecture, I'll explain how to make this the ground state of a Hamiltonian. What this is telling us is that with quantum mechanics adjoining some extra degree of freedom that we can discuss, we can encode the entire space-time history of a quantum computation into a single quantum state. Okay. Thanks.
So, yeah, let's thank Professor Laumann, and then
Okay. Oh, yeah.
Other than telling you everything the circuit did to an initial state.
It's easier to write down Hamiltonian, to write down Hamiltonian for this that matches the circuit.
Oh, so you can write down Hamiltonian that maps this onto a different QMA problem.
That's right. So So this clock state is going to be the ground state of the Hamiltonian we use to prove the I don't remember exactly how it goes, except I have seen it somewhere. Pretty cool.
So you can also just say, well, let me just apply the gates. So it's kind of a question what I'm doing is I'm hiding that computation which gates to apply in whatever it is that you're observing. Which also has I'm skipping that step to some.
也有可能通过，但是是被这个东西所放的引导，而且
这个 M 相当于是你测试的，是测试次数。
M 是你总的